Hello everyone and welcome to another Würth Elektronik ISOS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Wireless Power Transfer, Advanced Coil Knowledge. Our speaker today is Cem Som, who is working as Division Manager in the field of Wireless Power Transfer at Würth Elektronik ISOS. He will hold today's webinar and also answer your questions. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but are holding the webinar out of the home office. In case of technical issues or some delay, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at isis-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will receive the link to the presentation as well as to the recording of the webinar only in the next few weeks. And now I will hand over to our speaker, Cem, and I wish you an exciting webinar.
Hello and welcome also from my side. First of all, I would like to thank to Markus for this warm welcome words, and also to my colleague Jörg, who started the webinar day in the morning today, and he helped me to create the slides. Today's topic, wireless power transfer, advanced coil knowledge, will give you an inside view of our R&D work at Würth Elektronik ISOS. Today's agenda is quite simple. We have some kind of application examples which will show you today some possible ideas and techniques where you can use this technology. The coil physics will show how important is the sizes and in the end also the materials impact. The coil tuning in the end will give you and summarize this in the end for you. Applications. What kind of applications are very important for us and also for you? In the case, beside of consumer products, we have for sure the automotive area. In this picture, you can see an example from BMW, which shows in a YouTube video a very nice way how to transfer energy and charge your battery in the car. But not only the car charging, also the in-car charging is possible. That means that you are able to charge your mobile in the car. As a second or more or less infrastructure possibility is if you are in your office, home office, or in the normal offices, or in the train, airplane, or any kind of coffee shop, you are able to charge your mobile in the table if you have a hotspot. Additionally, very important is the medical area. In the medical area, we have the possibility to seal the product completely, which gives you the benefit that you're not depending on any kind of connectors. In the same way, it is for the industrial area, for rough and tough areas, which are dirty, which are wet, which gives you underwater applications for robots or any kind of cameras, for example. If we go now to a customer of us, which is in the medical area, this is shown here in a so-called cochlear implant sound processor. you will have as a possibility to hear again, or maybe you don't hear before, that your implant will be charged or energized from this sound processor, which sits outside your head. In this circle here is the wireless power coil plus the energy and data transfer included, which will activate the cochlear implant in the head. If we go now for an example to the consumer branch, you can see here the iPhone 8 and the iPhone 11. Both of them are using wireless power as a charging possibility additionally to the lightning plug. As you can see, the receiver coil on this left-hand side and also on the right-hand side is in the same size as the A11 coils and the used WPCC standard, which gives you a better efficiency and a better handling during charging. For the coil physics, which is quite easy to understand, but I would like to start first of all to show you the magnetic field inductor basics. A single inductor or conductor looks like in this picture that the magnetic field is around this wire. If you use instead of a single conductor a coil with several turns, the magnetic field will be inside of this tunnel, focused, and will be guided. If we look now as a rod core, for example, we will have inside of this air coil some ferrite material, which is defined the material by the permeability. We can have different kind of materials in the market. We can have iron powder, nickel zinc, manganic zinc, metal alloys. All these materials are used for different kind of applications, which are depending on the saturation, which is depending on the frequency, which is depending on the temperature. As just mentioned, some of these very important points, how to choose the correct material. Later on, we will have a closer look on that. The next point, which is important, how to define the inductor, is the magnetic area. As you can see in the picture, the magnetic area of the coil can be different for the same amount of turns. Also, if we have the same area, for example, we can have different kind of turns, which will give you a different kind of inductance value. Of course, the last point is the effective length. This effective length, if you can see here on the rod core, is that the length will be calculated in the middle of the ring. All these 4 components or 4 definitions will give you the ability to define the inductance. How this looks like in our wireless power transfer system. In our wireless power transfer system, it's here a very simple one, simplified schematic. A simple wireless power transfer system have a transmitter coil and a receiver coil. These 2 coils are like a transformer with a big air gap. It's like I'm cutting a transformer in 2 pieces, like the primary side and the secondary side. On our primary side or transmitter side, we will have for sure a source and some parasitics. On the receiver side or the secondary side, our parasitics and the load of the system. As mentioned in the middle, we have here these 2 coils, the transmitter and the receiver coil. They have the air gap at a distance d. They are coupled with the coupling factor K. As an example, the transmitter coil looks like this special shaped coil from Würth Elektronik. Important is that in a close coupled system, which we can see here, we have frequency in the kilohertz range, and the distance, as you have seen in the picture, is very short, maybe maximum up to 10 millimeters. We can calculate the efficiency in this system. We will have a quite complicated formula for that, but if we do it a little bit simpler, we can see that the maximum efficiency is depending on the coupling and the Q factor of the both coils. As higher the Q, as better the efficiency. We would like to try to keep the coupling constant and increase the quality factor of the coil system. As an example, we made some simulations for the figure of merit. That means to see a simplified diagram of the coupling and the maximum efficiency depending on the different Q factors. If we have a look inside of, for example, a Q factor with 25, and we will have a, for example, 0.5 coupling factor, we will get round about a 0.8 maximum efficiency. Just by increasing the Q factor from 25 to 100, we can see at the same coupling, we can increase our efficiency roundabout by 20%. If we go over Q 100, 200, 500, you can see there that there will be not a big difference. That means, in the summary, high Q factors will give you long transfer distances and a higher freedom of positioning. What means higher freedom of positioning? As an example, we will have a transmitter coil and a receiver coil. If in a simulation like we did here with the 2D FEMM simulation tool, we placed these two coils and simulate the coupling factor by changing the angular displacement. That means by 0, they are parallel to each other. We will have, for example, 0.95 a K factor, a coupling factor. That's great because an ideal transformer is at 1. Just by changing the angular misalignment from 0 degree up to 40 degrees, you can see that the coupling factor is just the half of it. So we lose 50% of coupling, which will have directly an influence to the total efficiency of the system. Additionally to the misalignment, which can be lateral or angular or vertical, we will also have an influence of the effective area, which I mentioned in my first slide. The coupling factor K can be calculated with this formula, for example. But now let's have a look into a system, for example. I would like to have an A10 or A11 coil, which will have this size of coil, means around about 50 millimeter outer diameter. Ideally, I would like to have an effective area which is the same, like for this coil as a receiver coil. The coupling factor will be here between these two coils, measured in the real system by 0.8. If we now go down with the effective area from left to right, we can see that the coupling factor is decreasing by around about 20% if the effective area of our receiver coil is just half of the effective area of our transmitter coil. So that means also the coupling is not only by the misalignment, also depending on the size of the coil. If you have a system you would like to use a G system with a transmitter coil, you have to take care on your receiver application side that the effective area on the receiver coil should be 1:1. This will increase your efficiency. This will minimize the charging time, for example. Let's have a look into the standard coils which we have in our program at Würth Elektronik. As an example, we have here 4 different kind of coils. These 4 coils have more or less the same inductance. As you can see, 7.5, 8, 7.9, or 10 microhenries. The sizes are completely different, you see, but also very, very important, and this is the influence to the system efficiency, is the coupling, the Q factor. The Q factor with this part is at 50. As you can see by the smaller parts, it's just 18 or 19. This is depending on the used material, which is here in the back in black. Here we have a ferrite full solid material. At these three parts, we have a thinner pre-braked or pre-fractured ferrite material. This is one important point which is influencing the Q factor, but additionally, which is also influencing the Q factor, is the way of winding the turns of the wire. In this case, we have a Litz wire with 24 single strands and 0.08 millimeter. This will causing a very low DC resistance. And of course, the Q factor is high. Now we go to a bifilar, which is 2 times 0.45 millimeter wires in next one by one. And here we have a thinner one. As you can see that as thinner the wire is, which you can see here, single wire, higher the DC resistance is, and directly the influence of the AC resistance. The AC resistance is here measured at 125 kilohertz, like the same like for the inductance and Q factor, as the AC resistance is really the working point for each of these coils in the system. At this resistance value gives you the losses in the system for the coil, which will end up by self-heating. Here we have a great graph which shows you the distances, working distances, and the coupling factors. If we choose the A10, A11 size transmitter coil, which we have seen in 2 slides before, and we're putting these 4 receiver coils directly on top by 0 degree without any lateral or angular misalignment. What we can see here, first of all, the Q factor of the transmitter coil is 180, so this is great, very high. For the other parts, as we have seen, there are also the Q factors in a lower stage. Now we can see as an example at 6 millimeter distance, which of these 4 types have the better coupling. Let's have a look. Normally, everybody thought about that this coil with the 45 Q factor should have the better figure of merit because it's the highest value. As you can see here, the figure of merit is 99 because it's multiplied by K, by the coupling factor, because of the coupling factor is lower than the part with the lower Q factor. But the part 207 in the end, which is this one here, have a bigger effective area. So that means the bigger effective area, one by one, like this one, have a higher impact than the Q factor of the smaller part. This is a very interesting point, that not only the Q factor is important, here is the effective area to each other very important. If we go in the other way around, if we are not using, for example, a Qi system, if we go into a system in a proprietary, that we can use the same coils as transmitter and receiver. So we will have, for example, again, 110 as a transmitter coil, but we use more or less also other coils which are used for transmitter side as a receiver with a high Q factor. And again, at 6 millimeter distance, we can see that the total figure of merit value is really, really high, as the coupling factor to each other is more or less the same because the size of the parts, effective area, is the same. So it's not depending the differences of the Q factor, which will end up by 7 to 8% lower. So In the end of the day, as bigger the ferrite is, here you can see the plate, and the Q factor is high, the coupling is high, the figure of merit is high, which will increase for sure the efficiency of the system. Now we have seen that the material have an influence. So which material we're talking about? As we have seen in the backside of the coil, we have a ferrite material. If we don't have a ferrite material shielding at the backside, the magnetic field around the coil in the air coil looks like that. With the shielding on the backside, we can see there will be a focused magnetic field on the top side of the coil. If we have two coils, transmitter receiver, like a transformer model, the magnetic field is focused between the transmitter and the receiver side, and around the two coils, the magnetic field is so low that you are able to place your schematic or PCBs or caps or batteries, which don't have any kind of influence, as the magnetic field is more or less zero. So which kind of ferrite materials we have in the market? Here you can see we have different kind of materials. This is the impedance, this is the working frequency. As mentioned in the beginning, we can have different kind of materials in our portfolio. First of all, I would like to start with the iron powder. The iron powder, as you can see here in black, is working in the lower frequency ranges and will drop down in the range of 1 megahertz. The next, it will be the manganic zinc material, which will also have a higher frequency range and can be used up to 10 megahertz. And the last one is the nickel zinc cores, which can be used up to higher frequencies and also up to frequencies up to 1 gigahertz, for example. So if we have now a system for wireless power transfer, which material we should use? Let's have a closer look to the datasheet of the ferrites. As an example, on the left-hand side, I just cut out the parts, the specification from the company Acme. The material is K081. That's a nickel zinc material. And the manganic zinc material, P41, also from Acme. As you can see, we have to compare not only the initial permeability at 800, for example, or 2400. Also very important is always that we have to look into the power losses. As you can see at the nickel zinc, at 25-degree power loss, at 150 millitesla, we have a value of 400 kilowatts per meter. And if we look into the manganic zinc, we can see the value is just 125. I know that this is 25 kilohertz and this is 50 kilohertz. Yeah, this is clear, but it's more or less in the same range. So it's quite low. Overall, both materials can be used for the wireless power transfer system. Important is that we have to use a low loss material and we have to look at the working frequency. For sure, if we are at 100 or 150 kilohertz, we can see with a 200 millitesla flux density, the material losses will increase. So it's very important to have a closer look at the working frequency, the temperature, and for sure, the losses. Let's have a look on the losses, which is important and how can I see them? In the data sheets of these two materials from Acme, we can see my mu prime and the mu double prime curve. The mu prime curve is directly influencing the inductance, like here, and the mu double prime are the AC losses of the core of the ferrite. So we can see, for example, also for the manganic zinc and for the nickel zinc material, that the mu double prime curve is really completely different if you are looking into the working frequency. So this is in kilohertz, this is in megahertz. This is, let's say, also one big issue which we have and which you have to closer look in the ferrite material, that they are comparing diagrams, but not in the same range. But anyway, we can see this is 10 kilohertz, 100, 1000. So if we are 1000, it's 1 megahertz. It's this range where the breakthrough is. And you can see the nickel zinc is after 5 megahertz. If we are 100 kilohertz, wireless power transfer closed coupled systems will be in this area. So the mu prime is stable, mu double prime is also very low. Also here we can see that the mu double prime is low. The same thing happens for the loss factor, which we can see here, or the power loss. Here we have a different values than here because this is the loss factor and this is the power loss. It's not the same calculation, but we can see for different frequencies, which is also here given, as higher the frequency, higher the losses. Also the same thing as for the 100 kilohertz range, and the higher frequencies of the working frequency, the losses will increase. This is important to know that these two are low loss materials for the low frequency. So it's not usable for gigahertz or hundreds of megahertz. This we can measure in our lab, for example, how this behavior is of the material as a shielding. We did this, for example, with EMI measurements on the backside of our receiver coil. How this looks like. As we can see, for example, 3 different kind of materials. So we have manganic zinc, nickel zinc, and this is iron powder. Now in these curves, you can see how the behavior of these 3 different materials are. The harmonics in the back, in the end, are not so important, but in the beginning, and we can see that type 1 with the manganic zinc have the lowest dBm amplitude with the manganic zinc material for this 100 kilohertz. Additionally to the material itself, of course, the shape and also the size of the ferrite on the backside is important. And for that, we did some kind of simulations. I would like to show you this. We do some FEMM simulation with ANSYS and Maxwell ANSYS 3D. And in this case, we choose a 5 centimeter or 10 centimeter round shape coil with 10 turns and 10 amps. And we see that there is around about 32 microhenry. As you can see in the picture, as we have seen it before, this is the ferrite, this is the coil, and the magnetic field is focused around that. Now, some of customers also have the request they would like to have a hole in the middle, because they would like to put it on a rotating system, or maybe they use it as a, if this is not so big, but is in a smaller case, if you would like to use it on your wearable or your smartwatch to place any kinds of sensors in the middle. How this looks like, what effect we will see. As you can see, with the same sizes, the same turns, and also the amount of power is the same, we have, just to go back, more or less the same inductance, no big change. The only thing which is important, which you have to take care, is that if you place this kind of coil with a hole in the middle, the magnetic field in the middle will also go through the hole, and you will have some influences for parts which are placed on the backside. If you are going to do that, you have to take care and you have to place an additional shielding material if you would like to place a battery or any kind of other circuits. Maybe the other point is you would like to go down and to minimize this ferrite material. In this case, it's also possible, instead of the full material, just to make some stripes. In this case, if you do just the stripes and minimize the ferrite material to the minimum what's possible, and same sizes, the same turns, same current, we have 25 microhenry. So there is a drop of 6-7 microhenry of the inductance, as the magnetic material is much lesser. And you can see also here the backside of the magnetic field on the ferrites is much more. So for sure, if you would like to place any kind of PCB circuit on the backside of battery, you have to have a shielding on that. An additional view is if we just have a look into this horizontal variation, is that the magnetic field looks more or less in the same like the first picture, only you have an additional field on the backside, which, as I mentioned before, could have an influence on your schematic. Also important, which I would like to mention in the end also, is of the coil, is the wire. What kind of coils, wires we are using in our products. We use, for example, single wires, which are very simple, cheap, and rigid, as you can directly wound them, and it's easy to do. Sometimes we're using also bifilar or trifilars, as we put single wires, 2 or 3 next to them, and make the turns around it. Means we have a more or less same height, but we will decrease the RDC, and the diameter will increase a little bit for sure. If you would like to reduce skin and proximity effect to be more flexible from the wire itself, then we use Litz wires. Then Litz wires have the positive effect that the RDC, the resistance, will go down. Additionally, if we would like to have a same height, but we would like to increase our possibility, more power to the same area, so we do bifilar Litz wires. This also saying it's reducing the skin and proximity effects, the diameter is the same, the height is lower, but for sure, both variation with the Litz wire are more costly than the bifilar or single ones. Let's go to the last chapter of today for the coil tuning. Important, of course, is not only standard products, also customer-specific coils are important in some kind of applications, as your application is very specific or unique. So yes, we do customer-specific coils. Important for us, if you go to our website, please fill in the inquiry sheet and help to understand your system, that we can design the best fitting solution for your system. The inquiry sheet is quite simple to fill in. This is a screenshot out of it. You can see that we would like to know the simple things like the switching frequency, the maximum currents, what maybe the needed inductance is, or the minimum Q values. If this is the things which you would like to know in your system for sure. Besides the electrical, we also would like to know the thermal specification and the mechanical specification, as these are very important to choose out the correct raw materials, like the wires, the ferrites, the glues, which will directly influence it. Also, the mechanical specifications are very important, as maybe we have to start new tools. Important is, if you would like to place and start a new project with a customized project, the point is how long it takes that you will get your new prototypes. Here, I try to show you our process in a very simple way. Normally, there is a request. This will take 1 day, as we will answer you and we will give you any kind of simulation of this if we would have to do it. Simulation takes more or less a week, that we will have a closer look. Then we will send you the feedback of the simulation. After that, we are happy to get your feedback. If everything is very good and fine for the simulation, we can do for sure our starting from new coil tools for ferrite shielding, and this takes 3 to 6 weeks. Then we need a 1-2 day run around that just to build up some prototypes and the first samples. If they are ready, they will be delivered from Asia to Europe, as all our wireless power transfer production lines are in Asia. So that means it depends. Also today, according to the coronavirus, everything is a little bit lower down. So that means a week roundabout is the delivery time. We will receive them in our headquarters or in our office in Munich, and we will do the first tests if all these simulated results we can see also at the prototypes. Then we can deliver them to you. Overall, we will have roundabout 8 to 9 weeks if we have all these kind of things to do. If we have a possibility to use the same toolings for the coil or for the ferrite, and it's very near to a standard product, or maybe we have already a tool available, then for sure the 3 to 6 weeks here will be shortened down. Important, what you have to consider. Use the largest possible coil. That means as the effective area is 1 by 1, you will have the best efficiency. Keep the distance in the range of the maximum efficiency. For sure, if you have the possibility to fix your transmitter and receiver design in that case that you will have the best efficiency, then the influence is as less as possible. The misalignment, keep it minimal, like angular, vertical, or any kind of horizontal misalignments. This gives you better efficiency as the coupling will stay the same. The best matching coil combination is, as I mentioned before, that the effective area and of course the transmitter and receiver coils have to fit each other. That means not only if you have a smaller coil, you have to choose a smaller transmitter and receiver coil. Be aware, of course, of the parameters which will influence, like the wire, the material, the Q factors. Everything is influencing each other, and you have to choose, or we will help you to choose the best products. In this case, we have the broadest portfolio at wireless power products in the market. If you would like to have more inside views and additional informations, please go to our wireless power website, www.we-online.com wireless power. There you can find a lot of informations according our development kits. You can find also our inquiry sheet for custom coils. You can have a closer look also in our trilogy of wireless power transfer book, where all these informations are in, and additionally, additional tools and supporting we will have here, like application notes and videos, for example. I would like to thank you for your attendance, and if you have any additional questions, I'm happy to be here for you.
So, thank you, Jim, for your interesting presentation. As you have mentioned, now we would like to turn our attention to your questions, and we wait a little until some questions come in. You can ask us the questions with the webinar control panel, with the chat function. You will find that on the right. If we are unable to answer them yet, we will answer them via email afterwards. So let's have a look at the first questions. Jem, why should the Q value of the coils be high?
So the important point is for sure the Q value, as I mentioned, is a part of the figure of merit. As higher the Q value, as better the coupling it is, and you can increase the distance or you can increase the total efficiency.
Okay, so thank you for your explanation. Then let's have a look at the next questions. Yeah, and here we are. Can the same coil act as transmitter and receiver?
Yes, this is also an important point that a lot of misunderstanding is there. If you have, for example, the transmitter coil or so-called transmitter coil and a so-called receiver coil. In the WPCC specification, the transmitter coil are specified from the size, from the Litz wire, from the magnetic or shielding materials. These are specifically specified as a transmitter coil because of the interoperability of the WPC and G standard. Important is, of course, that the transmitter coil or receiver coil can be used vice versa. It depends all on your application, and you can choose it on your own appliance if you would like to choose 2 transmitter coils or 2 receiver coils. So both of them are able to do.
Okay, thank you. Then as we have a look at the next questions, just a hint from my side, you will get the link to the presentation as well as to the recording in the next few weeks from us via email. So Jem, let's move to the next question. How does adding a thermocouple passing through the coil into the middle influence charging efficiency?
So that's, let's say, a very interesting question, as a lot of people are using the hole in the middle, which I mentioned before, to use any kind of sensors as a thermocouple or to measure, I don't know, different kind of things. The thermocouple in the middle, of course, is influencing the magnetic field, as it is like a foreign object. It's like a metal object in the middle, which will decrease the efficiency. But this depends, of course, on the size of the hole, of size of the thermocouple, if it is active or non-active. So there is not possible to say the efficiency will drop down by 1 or 10%. This is depending on every different kind of application and must be measured in the system.
Okay. So then we have a look at the next questions.
Okay, let's have a look at the next one.
Yeah. So it says, what is the delay in power transfer between Tx and Rx?
So if I understand the question correctly, the question is how much delay of the power transfer. So there is no delay because the magnetic field is on or off, and that means it is directly transferred. But for sure, in the reality, if there is handshaking, also in the WPCC standardization or in proprietary systems, we always have a kind of handshaking, which gives you an on-off signal, which gives you kind of interesting, let's say, more power, less power. So this is not a delay in this case, as the state machine is running in the background. So to answer the question is, there is no delay in case of power transfer. This is just controlled by the microcontrollers on the transmitter and receiver side.
Okay, so thank you, Jem, for your explanation. Then we have a look at the next question. So does wireless power work also in rotating systems?
Also, this is a very interesting and good question. For rotating systems, for example, we can use parts, which I showed in the simulation with a hole in the middle, which you can place. And important is that the rotating shaft is not a metal shaft, as metal in a magnetic field will minimize for sure or increase the proximity and eddy currents, and this will heat up. And this will decrease the Q factor and also the distance between the coils. So important is you have to place a shaft which is not non-metallic, and then you can just place the transmitter and receiver coils on the shaft and transfer the energy during the rotation, as the rotation looks like as the coils are just directly standoff and have a fixed place and fixed distance. So this is not a problem and is possible to do.
Okay. So then we have a look at the next question. Yeah, you just spoke about the distance. What is the maximum distance between transmitter and receiver?
Also, this is a important question for everybody, as everybody wants to know, okay, in which distances I would like it's possible to do. So in general, for the wireless power transfer and also for the cheese system, they are regulated. Normally, they're in the range between 4 and 8 millimeter, maybe maximum 10 millimeters, which you can charge your mobile. In proprietary systems, we can increase this distance up to 40, 50 millimeters. This is not a problem. Also for loosely coupled system, this is possible. Important point is always this distance between transmitter and receiver coil. They are really depending on the size of the coils, working frequency, and important in the end of the day also if you have any kind of foreign objects which must be detected. As bigger the distance, foreign objects can be placed in the middle of the field, and this is very dangerous. So for G systems, between 2, 3, 4, up to 8, 10 millimeters, proprietary systems working also for bigger distances.
Okay. So then we have time for one question more. So we have a look at them.
Okay. Let's do this one.
Yeah. So the last question, Jem, how long does it take to start power transfer between TX and RX coil from off state?
So this is a good question, as this depends really on which system you're working on. For G systems, this is a state machine. So I cannot give you now the milliseconds for that because I don't know that. But this depends on the semiconductor companies in which way they do the regulation and what kind of regulation is used for this. As I know, what I have roughly in my mind from G is around about 250 milliseconds. Could be less also. I'm not sure for that. But this depends really on your state machine. So this is nothing which the passive components like the transmitter receiver coils are influencing. This is controlled from the transmit and receive state machines and the schematic around it.
Okay. So thank you, Jem, for your explanations. And now we are finished with our webinar. If there are any questions left from your side, just email us on isis-webinar@we-online.com. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Jem, for this great webinar.
Thank you, Markus, and have a nice day.
Also from my side, have a nice day. Goodbye.